All right, so Module 8. Guys, we are talking about electrical today, and I am super excited to teach you guys electrical. Um, this is, to me, the most exciting module, and I'm going to tell you why that is. And this is a true story. Um, so growing up and, prior to going to school, I didn't do much. I hated electrical. I just hated it because I didn't understand it, and I have a real hard time, trying to dive into anything and work on anything that I don't understand first. And I didn't understand electrical, and I just had a bad taste in my mouth, kind of for electrical. So, anyways, I start going to school, and I don't remember. Electrical was like a few months into going to school, and I get to my electrical class, and I'm just dreading it. I'm like, geez, electrical. And I'll tell you guys, this is what I had in my mind going into that class. And I said, here's what I'll be. I'm going to be really good at everything else, and I'm just not going to care about electrical. So wherever I get a job, I'm just going to tell them, listen, I'm really good at everything else. Give the electrical stuff to somebody else because I just don't like it. I just don't like electrical. That's okay. So that was my attitude going into it. So get to my electrical class and get through the first couple days. I'm kind of just trudging along, and it's just not clicking with me. It's just not clicking. I'm trying, but again, I have this bad attitude to it, but I'm trying to kind of understand it and grasp it. I'm struggling with it. And there was one day that I'll never forget, sitting there in class, where it just felt like felt like a switch flipped inside my brain, and it all just fell into place, and it clicked, and it made sense. And I'll tell you what, guys, since that day, I love electrical, and I love troubleshooting it and repairing it. It can be really challenging, but it's also really rewarding when you figure it out. So I'm going to tell you, I'm going to teach you kind of some unique or original ways. I'm going to teach you electricity, and I'm going to tell you exactly what it was that made it click for me, and hopefully it will for you as well. But first, we're going to get started here and cover some of the basics. And here's some things that we're going to be covering today. So we got to talk about some safety items, of course, electrical definitions. We're going to be talking about the units of measure, all the different units of measure that we use to measure electricity. We're going to talk about the flow of electricity. We're going to talk about parasitic draw. There's a fancy word for you. We're going to talk about different ways to test, different electrical tests that you're going to have to do. And then finally, making electrical repairs. So let's dive right in. By the end of this module, you're going to be able to do that with your hands. Okay, that's a lie. But let's get going here. So let's cover some safety items a minute. First of all, battery acid. Some really nasty stuff. Can burn your skin. You get it on your clothes, and it just kind of slowly keeps eating away. And you get a little bit of it on your shirt. It's going to be a little hole. You look at it a couple weeks later, and it's a great big hole. And don't take this lightly. It is extremely damaging to the human eye. You get some battery acid in your eye, it's a big deal. You need to flush it out immediately. I mean, it can literally eat a hole into your eye. So you only get one set of eyes, right? So whenever I deal with anything with a battery, I like to throw safety glasses on because you don't want to screw around with that. You get battery acid in your eye, and you're going to be lucky. You're going to be lucky if you don't have long-term lasting effects. So, ignition coils. So spark plug. You're going to get zapped. It's going to happen to you. It's going to poke you. It's not going to hurt you. I've been poked probably 100 times. It's not going to hurt you unless you have some sort of a crazy medical condition or a pacemaker or something like that. I'm not a doctor, but I can't imagine that'd be good for you. So, hybrid systems. So with hybrid electrical systems, supposedly there's enough current in there to kill you. I've never heard of anybody actually dying while working on a hybrid, but I'm sure it can mess you up pretty good and supposedly kill you. But so on a hybrid, there's a low voltage and a high voltage side. The low voltage is going to have like a normal 12-volt battery, you know, like any other car. The high voltage side is typically in the back, like in the trunk area somewhere. When you have to, and if you have to service these systems, they make a really thick rubber glove, and these gloves have to be like serviced or tested every couple months to make sure there's no cracks in them. You have to wear the appropriate rubber gloves to insulate your hands when working on a hybrid system. Also know what you're doing, because you don't want to just go in there and start fishing around, and so just be careful if you ever get to a hybrid electrical system. Learn what you're going to do before you start doing it. And finally, shorted wires can get red hot and possibly start fires. So something to think about too. Yeah, wires can catch fire if they get hot enough, which is why they put fuses on everything. Okay, let's talk electrical. Now, just like the rock band AC/DC, there are two types of electricity: alternating current, which is AC, and direct current, which is DC. AC, or alternating current voltage, is what you're going to have in your house or your apartment. It runs off alternating current. Alternating current comes from, ultimately, from a humongous generator, and then it's, you know, pipelined all the way to your house. So alternating current. Now I have these little, let's see here. I have these little diagrams right here. This is what on a graph or on a oscilloscope, which is basically just an way to graph electrical voltages, also called just a scope. Alternating current looks like this, a wavy pattern. Now DC, or direct current, only comes from a battery, and all the stuff you and I are going to have to worry about is going to be direct current. But I wanted to explain the difference. Direct current is a steady, solid, straight line across if you graph it. So everything on your car is going to be DC voltage. We don't have to worry about, well, one exception I guess I can think of is newer cars. They are coming with a 110 electrical outlet for plugging in phone chargers, whatever, but I haven't had to deal with that yet. You know, there's going to be a converter somewhere mounted in the car. I haven't had to deal with that yet, but 99% of everything you have to deal with is going to be direct current. And finally, direct current is much safer than alternating current. 12 volts will not hurt you. Now, if you go stick your hand in an electrical outlet in your wall of your house, that's you're going to get hurt. You should know that. Hopefully you do. But your DC voltage in your car, so you can take your two fingers, touch the negative terminal, touch the positive terminal. You're not going to feel anything. 12 volts will not hurt you. Okay, so let's talk about some different electrical definitions. So EMF stands for electromotive force. And what that is the electrical pressure measured between 2 points, measured in volts. So an example, a car battery should have approximately 12 volts from the positive to the negative terminal. So what we're measuring there, EMF, is the amount of pressure. Polarity. Polarity is the electrical pressure points or poles referring to the positive and negative terminals. Current. This is one we're going to use a lot. Current is the amount of electrical flow measured in amps. So the amount of flow measured in amps. And I'm going to explain this all again in just a little bit. But, okay, we'll keep going here. Resistance. Resistance is the opposition to current flow measured in ohms. Another little note there is resistance can create heat. So typically if you have something with high resistance. Say you have a faulty switch or something like that, and if it's got a lot of resistance, typically it's going to also have a lot of heat. Okay, another electrical definition is continuity. Continuity is the ability of a circuit or object to flow current. So can you flow electricity through it? Example, a copper wire is obviously a really good conductor versus a piece of wood. A piece of wood's not going to conduct electricity. Now, one other term that I don't have mentioned here is, I want to start off by just talking about what is electricity. Electricity equals the movement of electrons. So we have electrons moving ultimately from our positive terminal to our negative terminal. The positive electrons, positively charged electrons want to get to the negative terminal so bad. That's all they want to do. And we harness that power. We harness the that movement of electrons, and we create we can make it do work for us. We harness that and we make it do work. Okay, so let's look in units of measure. Voltage. Now voltage, guys, equals pressure, the amount of pressure. So when you have 12 volts coming out of your battery, that's a voltage is the amount of pressure. That voltage reading is how much pressure basically we have between terminal to terminal. It's one way to describe it. Almost all of your voltage testing will be in the 0 to 14 volt range. Millivolts. Millivolts is 1 volt equals 1,000 millivolts. So millivolts, the only thing I can think of off the top of my head that reads in millivolts right now is O2 sensors. So if they read it, basically O2 sensors read in a 0 to 1 volt scale, but we want to see that in millivolts. Resistance. Almost all of your resistance testing will be in the 0 to 10 ohms range. Remember, resistance equals ohms. We call that ohms. Resistance is the opposition to current flow, measured in ohms. Milliohms is 1,000, 1 ohm equals 1,000 milliohms. So milliohms is a super low resistance. Mega ohms, on the other hand, 1 mega ohm equals 1 million ohms. So mega ohms is super high resistance. We probably never have to deal with this stuff. The only time, in circuit boards, that type of stuff, where there's resistors, that's where they get into the mega ohms, that type of thing. Okay, so I got a video to show you guys now, and I hope it helps, because it's going to show you a totally different way of thinking about electricity. So take a look. Alright guys, so try not to laugh too hard at my little illustration here, but we're going to use water to represent electricity, and I'm going to teach you guys in a way I guarantee you've never been taught before on the movement of electricity. So when it comes to electricity, there's a lot of similarities between electricity and water, believe it or not. Because if you look at the two tanks we have here, we have a 5-gallon tank and a 500-gallon tank. That's going to represent voltage. Voltage equals pressure. Now let's back up a minute. Electricity equals the movement of electrons. Okay. So we know the electricity equals the movement of electrons. We can harness that electron movement and create, and make it useful for turning on lights, that type of thing. Voltage equals pressure, the amount of pressure. So we're going to call this little 5-gallon tank over here a AA battery. That's not very good, but anyway, let's call this 500-gallon tank over here. We're going to call this a 12-volt battery because there's more pressure in a larger battery or in a larger voltage. There's more pressure there. Okay, so looking at this illustration here, we have our water. These little round things here with the lines coming off of them, those represent water wheels, or in this case, an electrical load. That's our electrical load. So let's get started and talk about the little 5-gallon tank here, 5-gallon bucket, and you can see we have a little valve right here, and we're going to go ahead and open that valve. Water starts pouring out, and it's going to spin our wheel. It's going to start spinning our water wheel. So another electrical term we talked about is current, and that is the amount of flow. So look at the valve we just opened right here. That's our current. We have a small amount of flow. We have a small amount of water coming out of there. So that small amount of water is coming down, turning our wheel there, which we have a AA battery, so that's going to be our electrical load. We're going to have to pick a pretty small electrical load, so let's call that maybe a flashlight. You got a AA battery powering a flashlight bulb. So it's turning on that bulb. The wheel's spinning. The wheel is our electrical load, so the wheel in this case would be our flashlight bulb. And you can see that water wants to come straight down, and eventually it wants to fall all the way to the ground. Same way a battery works. The positive electrons start at the positive battery terminal, but all they want in life is to get to the negative terminal, or the ground. They want to get back to the ground. That's all those electrons want. They want to get back to the ground. So the same way this water is, that water wants to find its way to the ground because of gravity. So it's going to do whatever it can to get there, even if it means going through an electrical load here. So okay, so now let's talk about this 500-gallon tank. So we got a big 12-volt battery in here, and I got 2 valves on this tank. So let's start by opening this little valve. In the same way that the 5-gallon tank did, it's a small amount of current, so it's going to be operating a small electrical load here. So we can call this your running lights. You know, turn on your running lights. It's a small load. You open this valve. Remember, the water wants to get to the ground, or the voltage wants to get to the ground. So open the valve, start spinning the wheel, lights come on, water comes all the way to the ground. Okay, so now let's close that valve. Now let's go to the great big valve here. Now another electrical term we used was current. Current equals the amount of flow. So looking at the size of this valve here, we obviously are going to have a lot more current coming out of that water tank. A lot more flow. So that means we need a lot more electrical flow if what? If this electrical load right here must be a really high amperage or high current drawing load. So we're going to consider this to be like an engine starter, for example. So your starter is going to draw an amazing amount of amperage or an amazing amount of electrical force to use it. And you can see by opening that big valve, it's dumping a lot of water in order to spin this wheel. And in turn, how long do you think you can have that valve open before the water runs out? Probably not very long. Look at this one. How long can you leave that valve open before the water runs out or the voltage runs out? Probably a really long time. You can probably leave that going for hours and hours. This one, maybe a matter of minutes. So again, our water or our voltage wants to make its way to the ground. Our water just wants to get to the ground. Gravity wants it to. And we're going to harness that energy and make it do some work. So guys, it's the exact same way when we talk about a battery in a vehicle, harnessing the electricity and making it do work. So we're going to hop back over to our slides and continue to go over that. But I thought this was a really cool way to illustrate that a little bit, and I hope it helps. So also leave me some feedback. I'd like to know what you guys think of this. Series circuit versus parallel circuit. So this is just some simple stuff that I wanted to explain to you guys. A series circuit is a circuit which the electrical loads are arranged in a chain. So there is only one path for the current to take. So let's look at this. This right here is a series circuit. So we only have one path that the electricity can take. So guess what happens if one of those light bulbs burn out? None of them are going to work. Say this first light bulb burns out, you're done. None of these lights are turning on. A parallel circuit, on the other hand, is a circuit that has two or more paths for the current to take. If one of the loads or the light bulbs fail, the rest of the circuit will still work. So watch this. We have positive electrons going through the loop here, turning on the lights, and coming back. So what happens if this bulb burns out? Who cares? The rest of the bulbs are still going to work. No matter which one of these bulbs burn out, the rest are still going to work. You could even cut this wire right here and cut this wire right here. The electricity, or the electrons, still, no matter which bulb burn out, still have a path to ground. So one real good example of that is Christmas lights. And if you guys are old enough, you'll remember that old style Christmas lights. If you had one bulb go out, the whole length or the whole row of Christmas lights, that whole cord, none of them are going to light up. Nowadays, Christmas lights are come, and guess what? They got smart and they started making them all parallel circuits, so you can have one bulb burn out and it's not going to turn off all your lights. Okay, stop right there. So before you guys get overwhelmed, we're going to take a step back, and I'm going to try to ease your minds a little bit. And I'm going to give you the secret to understanding electricity. At least for me, this was the secret that kind of unlocked the door for me. So going back to my story earlier, I'm sitting there in class and I'm getting kind of frustrated. Teacher's explaining the electricity flow, and he's just, I'm like, okay, I kind of get it, but it's just not all there. It's not making sense to me. So right in the middle of one of his, lectures, I raised my hand and I said, I just still can't quite understand this. And I said, he's like, what don't you understand? And I said, well, for example, I said, how about an electrical sensor? I said, there's hundreds of sensors, right, on a vehicle. And I said, how do they work? How does an electrical sensor work? For example, an oil pressure sensor. How does that work? How does it tell the engine how does it tell the computer that the engine's making 25 psi oil pressure? That just didn't make sense to me. And he stops for a minute and he goes, okay. He goes, electrical sensors are nothing, are you ready for this? Electrical sensors are nothing more than a voltage in, voltage out reading. Huh. He says, I don't care what sensor you have, oil pressure, O2 sensor, fuel gauge, you name it. I don't care what sensor you have, all it is a voltage in, voltage out reading. So think about that. Your oil pressure sensor, how does that work then? So your computer sends 12 volts to the oil pressure sensor. The oil pressure sensor is designed to change the amount of voltage that comes back out of it. So based on the amount of pressure that sensor has against it, there's something inside of that sensor that spits out a different voltage. So say we got 25 pounds of oil pressure, say that sensor spits back 3.8 volts to the computer. The computer sees, okay, 3.8 volts, that means to me that we're making 25 psi oil pressure. So that's what That's what it's going to tell the computer. You plug in your scanner, that's what it's going to say, 25 psi oil pressure. So all that sensor did was take the incoming 12 volts, and it's a resistor, and it just changed the amount of voltage coming back out of it and sent it to the computer. That's it. So as soon as he explained that to me, it was like somebody lifted a 500-pound weight off my shoulders, and it was just like, wow, okay. And from then on, I had the mindset, I get it. I can tackle electrical. I can understand it, and I can beat it. And from then on, it's just kind of been like a fun challenge to me. Every time we get an electrical problem in, I love to troubleshoot and figure that out. So anyway, that really for me was the aha moment, I guess you'd say. Another thing I just wanted to tell you guys is don't get overwhelmed by the mess of wires in a vehicle harness, and it's easy to do. You got an electrical problem, you're like, oh great, I think I got a problem on this wire. This wire goes into a wire loom that's 2 inches around, surrounded by who knows how many wires, surrounded by another 100 wires, and it goes through the firewall or into the frame. How am I supposed to find that wire? Well, just relax, because there is more than one way to skin a cat, if you ever heard that phrase. And there's a few tricks that, we'll kind of teach you along the way, and you'll learn on your own too. But for example, I had one the other day. It went into a really humongous wire harness. I'm like, well, okay, here's one end of the wire by the computer. The other end's supposed to come out here by the accelerator pedal position sensor. I got a problem somewhere between there to here. I have no idea where that wire goes. In the between the computer and the throttle pedal, I have no idea where that wire goes. So guess what? I just ran a new wire. Ran it along, ran it through the firewall, tucked it in there nice, and ran it to the computer. So I cut the wire at the computer, tapped it in there, cut the wire at the throttle position sensor, and tapped it in there. Why not? You just eliminated that whole harness, where it goes through, but it's okay. You cut the wire, so you gave it a new path to travel on. That's still a professional repair, whatever we got to do to get stuff done. So it would have took hours upon hours to probably cut that harness apart to find the bad spot. So electrical repair, I went from the mindset of having I don't want to touch it to now it's like, think about electrical repair. It's not back-breaking work. It's clean. You're not getting full of dirt and grease and grime. For the most part, it's clean work. And again, it's pretty rewarding when you figure something out. Another thing to mention is when it comes to electrical repairs, 90% of the time you're going to spend on it is diagnosing it, and about 10% of the time is actually the repair. So usually the tough part is finding the issue. Once you find the issue, usually the fix is pretty easy. Alright, so we're just going to talk about measuring voltage, and what we see here is a multimeter. So you're going to learn to use these multimeters and for different tests. So we're going to go over some of the basic tests for you. So measuring voltage. You want to check your battery voltage. So here's our symbol for, there we go, our symbol for voltage, volts DC. So right here we have volts DC on the meter. So I circled that for you. You're going to click right there. These holes right here are where you're going to hook your meter leads to. So you're almost always going to use these two. The black one that says COM, that's common ground. So you hook your black meter lead to that. Your black meter lead always goes there. This one right here, see, it has the V, it's got the horseshoe, and it's got that little, kind of hard for you to see, but that's a diode symbol. So that's voltage. That horseshoe I was referring to as ohms, and then diode. So you don't really need to know too much about diodes, but voltage and ohms are going to be the majority of what we use. So we always plug into these two holes. Okay, volts AC. If you do have to use volts AC, that's the symbol for volts AC, the squiggly line on top. So you just, same way as volts DC, but you click your meter to the volts AC position instead. Okay, measuring resistance, or ohms. Right there you got that, so you're going to click your meter up, still using these two holes, and you put your meter on a circuit and it's going to tell you how much resistance is in a circuit. Any given circuit should have no more than 0.5 ohms. A good circuit, we consider a good circuit to have about 0.2 ohms. And when I say circuit, I mean an electrical connection from point A to point B. So for a headlight circuit, you want to have good voltage between, say, the headlight relay and the headlight itself. So you plug your meter on one end, on the other end, you want to have 0.5 ohms or less. And it's not the end of the world if you have 0.6, 0.7, or 0.8, but that's what we like to see anyway. Measuring amperage, now things are a little different. See, we have the, we're using this far left hole right here. You're going to click your meter all the way to A for amperage. Your black one stays here, your red one, meter lead, goes over here to measure amperage. And remember, amperage is the amount of current an electrical load draws. So if you need to measure amperage, that's how we do that. Okay, measuring a voltage drop. So what this is a voltage drop is the measurement of the lost voltage through a section of a circuit, or an example of a connector. So basically what that is using your meter to measure a voltage drop. Set your meter to the voltage setting, place 1 meter lead before the connector, or the area you want to test, and 1 after the connector, or the area you want to test. Your reading is going to be your lost voltage, or what's called a voltage drop. Okay, let's just give you an example here. You have a connector that you're unsure of, you have some wires running through this connector, you know, I don't know, example, go into your headlight, and you want to see your headlight, say your headlight's a little bit dimmer than you think it should be, so you measure voltage at the headlight bulb socket and you only got 11. So you're like, where did that voltage go? So here's an example. You want to check the connector. There's a harness connector near the headlight. So you tap into it, you stick your meter into the wire before and after that connector, and your meter says 1.5. 1.5 is referring to the amount of lost voltage between, or the amount of lost voltage going through that connector. So that reading is your voltage drop. You lost 1.5 volts through that connector, which of course is a bad reading. You don't want to lose more than, you know, something like that. You never want to lose more than 0.5. Okay, parasitic draw, measuring parasitic draw. So what the heck is parasitic draw? Does that mean your vehicle has parasites? Nope, parasitic draw is just a fancy name or a fancy word for a battery draw, or something drawing on the system. A parasitic draw is an abnormal, constant draw of power after shutting off the vehicle. Example, the vehicle's battery goes dead overnight. So now there's a couple different ways to measure this parasitic draw. Before we talk about the different ways to measure it, one thing you need to know, most vehicles need time to go to sleep after being shut off. So if you are measuring parasitic draw on a vehicle, it can take up to 20 minutes, depending on the vehicle, to allow all of the various modules to shut down. So when we say go to sleep, it means that these modules are still awake for a period of time. So what I mean by that is you shut your vehicle off, you turn the, you take the key out of the ignition, you slam the driver's side door, and if we're measuring battery draw, you're still going to see a draw for the first 5, 10, 15, up to 20 minutes. Well, these modules go to sleep. So all your modules, the PCM, powertrain control module, the transmission, even the instrument cluster, they all are still awake or active, and slowly they one by one start turning off or going into a sleep mode. So before we can get an accurate parasitic draw reading, we need to allow the vehicle time to go to sleep. Okay, an acceptable draw is 0 to 0.1, sometimes 0.2, but 0 to 0.1 amps is really an acceptable draw. A 0.5 amp or half an amp draw is going to drain a battery dead overnight. So that being said, a 0.25 amp draw is usually going to take about 3 to 4 days to draw a battery dead. Okay, so measuring parasitic draw. Let's talk about the first way to measure parasitic draw. Okay, so you're going to take your meter and you're going to set it to the amps DC mark. On my meter, it says 10 with an A and the DC mark. Remember, the straight with a dashed line under it. So 10 amps DC. That means it's a 0 to 10 scale. Anything over 10 amps, I can't read with this meter. So set your meter to the amps DC. Remember, take your meter leads, hook the one to the black common port and the other one to the far left amperage port of your meter. Okay, connect your positive meter lead to the negative terminal of the battery. Connect your negative meter lead to the negative end of the battery cable. So does that make sense? You're disconnecting your vehicle's battery cable, the negative battery cable. You're taking it off and you're basically putting your meter in line. So you're taking your positive or red alligator clamp from your meter, you're attaching that to the negative terminal of the battery. You're taking your black clamp and you're putting it to the negative battery terminal end, so the negative side of the wire. Now you can measure the amount of draw. Remember, you're going to have to get out of the vehicle is going to need time to go to sleep. Also, be very careful when you have your meter hooked up not to start the vehicle, or you're going to blow an internal fuse in your multimeter. It's not a huge deal. I mean, you can take your meter apart, like my Blue Point, you can take it apart, and I believe it's a 10 amp fuse, just a little glass fuse you can replace. But there's one downfall to using this strategy, using this type of test, and that is when you disconnect that negative terminal and hook up your meter, sometimes there's not enough connection there, because now you're using your meter to be the lost link between the negative terminal and the battery. Sometimes there's not enough current there to allow the vehicle to energize enough to turn the modules on and then allow them to go to sleep. So I don't know if that makes any sense to you, but so sometimes you have to actually unhook the battery cable, hook up your meter, touch the battery cable back together. I like to then have a helper turn the key on, turn the key back off, shut the door. Then I'm just touching them together now. I'm just touching the negative battery terminal to the negative battery cable. Now I can just let them loose again, and now your meter will read your amperage. So that brings me to the next one. The second way we measure parasitic draw, and this is my preferred way because it's a lot simpler, is by using a shunt. So a shunt I have there in the upper right hand corner. So the second way we measure parasitic draw again, unhook the negative battery cable. Now we're going to hook up a shunt. What is a shunt? A shunt is a pre-measured jumper cable, basically, between the negative cable and the negative battery terminal. Okay, so you pop the negative battery cable off the battery, you hook this up in line. And guess what? By using this thing, you can do whatever you want. You can start the vehicle, you can drive the vehicle if you want. So I like to hook this bad boy up. I like to start the vehicle, shut it off, just like you were done driving it for the day. You know, you take the key out of the ignition, you shut the door, and then you let it go to sleep. So, but here's what's crazy about using this. Now you set your meter to millivolts. Okay, so now remember, we need our meter leads, black in the common one, the red to the far right, like we were gonna measure voltage. The spot it usually goes, the far right. Now the voltage, just like you're measuring battery voltage, on my meter, one click left is the MV symbol for millivolts. Now set your meter to millivolts. Okay, hook up your meter leads. Hook the positive meter lead to the negative end of the shunt, and the negative meter lead to the positive end of the shunt. And it doesn't really matter if you switch them around. Put them one way, you're going to get a negative reading. Put them the other way, you're going to get a positive reading. But either way, you're getting the reading, so it doesn't really matter if it has a little negative mark in front of it or not. So now you can start the vehicle without worrying about blowing a fuse. You know, you don't have to worry about blowing your meter fuse at all using it this way. Again, allow the vehicle to go to sleep and then read the draw. Now the first test we talked about is a little bit more accurate. It can read on a smaller scale than the shunt method. What I like to do is, if I'm using the shunt, I hook everything up to test to make sure everything's working right. I like to open the door, and all of a sudden you see that you have a 0.4 amp draw. Like, okay, that makes sense. You shut the door, it starts going down, goes all the way down. If I get my readings all the way down to 0.1, I'm going to say there's really not too much of a draw in the system. I think it's okay. If it goes to 0, I know it's okay. If it's at 0.2, I think we got a draw in the system. So then what you're going to want to do, and I don't have this in the slides here, but so if you have a battery draw and you verify it using your meter, let's say you find that this vehicle has a 0.3 amp draw. So now what do? Well, here's a pretty awesome tip for you. Grab a pair of needle nose pliers and start pulling fuses. Start with the underhood fuse block, pull all the fuses one at a time, look for that battery draw to go away. If none of those change, go to the driver's side door, open the door. Now with the screwdriver, you're going to trick the vehicle. So with the screwdriver, push the latch back closed so the vehicle thinks the door is closed. Again, start pulling fuses one at a time. Eventually, you're going to pull one fuse out and that draw is going to go away. Bingo, you just found the circuit. So all of a sudden you're like, whoa, draw's at 0. Okay, what fuse is this? You look at your diagram. Aha, this is the radio fuse. So now I know my radio circuit is causing the draw. Guess what? You look at it, oh, it's an aftermarket radio. Somebody stuffed an aftermarket radio in this thing. Guess what? It's a problem. It's causing a draw. So you call the customer, yep, it's your radio, get a new radio. You should be fine. We can put a radio in it for you. Or you can leave the fuse unplugged and no more draw. So we talked about the shunt. So I got some instructions on here if you guys want to make your own shunt. Because you're not going to find this in a store. So that's the only negative. And to be honest with you guys, I don't even know how it works. It's a pre-measured, I don't even know who figured it out, but it's a pre-measured length of wire, and by using it in millivolts, you're actually reading amps. Seems kind of crazy to me. All I know is that it works. So I don't know how it works, I just know that it works. That's science. Anyway, piece of 8 gauge wire, it's got to be 19 inches long. And you can see right here we have some bare spots, and that's giving you room to hook your meter leads to. So strip approximately 1.5 inches of the insulation off both ends of the wire and crimp some alligator clamps to the end. Now, so you can build your own, you guys, or actually started building these things and have been selling them. So there should be a link at the bottom of your screen, and you can click on that, and if you'd like, you could buy one right for me and I'll send it out to you. Anyway, so let's talk about testing a starting charging system test. Alright, one of the most common electrical tests that you're going to have to do for a vehicle is a starting charging system test. Step 1, perform a battery draw test. So there are different types of battery testers. Analog, digital. This one here is an example of an analog. A digital one's going to be, you hook it up, it's going to ask you for the battery size, this and that. You hit enter, it analyzes the battery and it spits out a reading. I grabbed this thing first, guys, because it's just plain and it's simple and it shows you. There's a little toggle switch right here, or a big button you push. You hold it for 10 seconds, and hold it for 10 seconds, and these things start glowing red hot in here, and it's going to show you. You hook it up to your battery. It's going to show you your 12 volts. Hit your button, and it's that there's a little dial there, and it's going to go way down, and it's going to tell you if your battery's weak or not. So I prefer grabbing these first. Okay. Step 2. Use the battery tester to load test the starter. Again, you can use this kind or an electrical, or the digital kind. Have somebody crank the vehicle for you, and you watch the amount of load. You watch how much the battery drops. If the battery drops more than a specified amount, you have a starter that's worn out, that's drawing too many amps. Step number 3, test your alternator. You can do this using your digital battery tester. It's going to also analyze your alternator, or just throw your multimeter on while it's running. Watch voltage. You should be in approximately 14 volts running. I would say 13 to 15, give or take, but you see battery voltage come up when you start it, you know your alternator's working, right? Okay, we're almost there, guys. I know we got a lot to go over here, and I hope your brain's not smoking yet, but we are almost done. So, a relay solenoid operation and testing. A relay and a solenoid are basically the same exact thing. Generally, a solenoid is physically larger than a relay. So what the heck are these things? A relay or solenoid is a switch that is used to turn on or something of high amperage. So headlights, AC compressor, starters, anything that draws a lot of amperage is going to use a relay. A relay uses electromagnetic force to apply or release electrical contacts. So why do we use relays? So that a very tiny switch or very tiny wires can turn on a very large electrical load. So let's think about that for a second. If it weren't for relays, you would have what looks like a large circuit breaker inside your vehicle to turn on your headlights on and off. You'd have thick wire running all the way to your dash, and you'd have some sort of a heavy duty, maybe one of those things like you have to actually flip a lever to turn on, you know, you've probably seen those on TV, to turn on an electrical system. So to simplify everything, they use relays. Now you can just use a tiny switch, you can use tiny wires going to it. So a tiny circuit can control a really large circuit. The electromagnetic force applies or releases the electrical contacts. So if you see this right here, there's a little spring-loaded arm, when that relay energizes, it's just going to click. And what's happening in there, I got a couple different diagrams here. Here's one of them. So imagine these are our wires going to the relay, or here you got the little pins of the relay. But imagine the wires going right into it. Here's our two large wires, here's our two small wires. So these small wires, they're going to run to, let's talk about like headlight circuit. So these small wires are going to run to your headlight switch. You turn your headlight switch on, you now energize these wires, and this is a coil of wire. And one thing neat about making a coil of wire and energizing it electronically is it turns into a magnet. So you turn your switch on, it magnetizes this. Now this right here, this T-shaped thing is actually like symbolizes an actual bracket inside the relay. So you turn it on and it's going to magnetize this and it's going to click. The magnet is actually going to pull this piece of metal down. It's going to click. Now when it's clicked, you have a contact here, an electrical path here, and another contact here. So now you just turned on, say this is our hot wire coming right from the battery. It hops across here, say this goes to the headlights itself. Now you just turned that circuit on. Using small wires, you just turned on a large wire circuit. Same thing over here. This is more of a schematic, but you can see the battery, you can see a switch, you can see the coil of wire, and in this one it actually magnetizes. You can see right here is the switching rod. You energize it and it's actually going to magnetize it and push the polarity. Is going to push this arm away, pushes it away, clicks there. You just connected these two wires, you just turned on a circuit. Kevin. Okay, the easiest way to test a relay is to jumper the small leads and ohm test the large ones. So imagine we have this relay. Okay, let's look at this one. Usually they have a little, this is a bad example, usually they have a little schematic stamped right on the side of the relay telling you what wires are what. So you can take your small wires, let's pretend these silver ones are the small wires, you jump that. So you take a jump box, you take a battery, whatever, you put power to one, you put ground to another one, it's going to click. Now, take your meter, ohms test from there to there. Do you have a connection? If so, how much resistance do you have? If you have less than 0.5 ohms, I'd consider that a good relay. If we have higher than that, or if we have no connection at all when that relay clicks, we have a bad relay. Now relays don't go out that often, but it's important to know how to test them. Okay, which brings us to testing a starter. Because a starter has a relay built into it. It's called the starter solenoid. It's built right into the starter. So to test or diagnose a starter, we're going to talk about a no-start. A vehicle comes in with a no-start condition. The quickest way to do it is actually by grabbing your 12-volt test light. Okay, so you grab your test light, you get to the vehicle. So we're first going to check the two large solenoid leads. Here's a large solenoid lead and here's a large solenoid lead. This one here is tiny. So you're going to see that on every starter. Okay, so one of these large leads should have 12 volts that comes directly from the battery. So that 12 volts is there at all times. On this starter, just by looking at it, I know it's this one. So this thing's going to have 12 volts 100% of the time. I don't care if the key's on, off, on the seat, I don't care. It should have 12 volts all the time because it's hooked right to the battery. The other large one should have 12 volts when the starter is supposed to turn on. So when your key is in the start position, you should have 12 volts here, because what that solenoid is doing is transferring voltage from here to here. The small wire, or what I call the trigger wire, should also have 12 volts with the ignition in the starter position, in the start position. So remember, the small wires control the big wires. So you turn the key to the start position, that should have 12 volts. it should cause that solenoid to click, and now that should have 12 volts. So here's what happens. You got a no start condition, you go to the vehicle, I'd grab my meter, hook my alligator end to a ground, hook my pointy end, touch it right there, meter lights up. I grab a helper, I said okay, I touch it right here, so okay, go ahead and turn the key. He turns the key, boom, the meter lights up again. Okay, put my test light right here. So go ahead and try to start it. He turns the key, nothing. So what does that mean? We know this works, so we know we have a signal from the key. We just diagnosed a bad starter solenoid. So in that case, we just replace the whole starter. Nobody replaces just the solenoids anymore, you just replace the whole starter. So what you can see right here is this lead actually has a wire that goes right into the starter. So that's how that works. So a way to kind of cheat or trick the system, and I'm not necessarily recommending this, but it does work, you can jump a starter solenoid. So if you take a screwdriver or some metal object and touch this to this, it's going to make that starter turn. So you can jumper a starter by connecting those two together. Just a little FYI. Okay, testing an alternator. We're going to whip through this stuff pretty quick. So there's multiple ways to test an alternator. Here's what I like to do. Okay, so if a vehicle's not charging at all, I'm just going to be honest with you guys, 99% of the time the alternator's to blame. Now some people might get upset for me for saying that, but that's the truth. You got a vehicle that's not charging, 99% of the time it's the alternator, because that's the wearable part, right? I mean, yes, it can be the PCM or ECM not giving the correct command. Yes, it could be a wire harness issue, but alternators are a wearable part. So most of the time, you got a worn out alternator. Check your belt, because your belt drives the alternator. So check the serpentine or alternator belt, examine the connectors. If nothing seems out of place, assume the alternator has failed. And again, if you get a job somewhere, your service writer, he might not agree with this, but guess what, guys, that's what I do, because you can spend all day testing the system. Just call it a bad alternator. If the slim chance that you put a new alternator in and it still doesn't work, well, then you can go to the next step and diagnose a bad PCM. I always figure it this way. Pretend I get 50 vehicles in that have a charging issue, and one of them isn't the alternator, 49 of them are the alternator. By the time I get to that 50th one, I'm going to have saved so much testing time that I could buy 10 alternators. I'd already have saved at least 10 hours of testing. So that's my way of thinking anyway. Okay, so if you suspect an alternator to be weak, you can use one of those electronic battery testers to run an alternator test. It's going to check output, it's going to check diodes, and it's going to give you a result, alternator passed or failed. So again, using the digital multimeter, let's check to see if the alternator's what kind of voltage the alternator's putting out. So with the vehicle running, check battery voltage. A normal operating system should be about 14.4 volts. So that's going to be a good alternator. Alright, so here's an example of an electrical schematic, and you guys are going to have to learn how to read these schematics. What this is, it's basically a map of the electrical circuits, including the wires, the wire colors, connectors, and switches in any given circuit. So I know you guys can't see this one very good, but this one is an example of a fuel pump, and we can follow our power source going through the fuel pump relay. It comes up, it goes down, finally makes its way to the fuel pump motor itself. So I'm going to have a better example of this in my bonus video on Identifix training. We'll pull up a schematic and kind of walk through it a little better and show you guys how to follow them. So check out that bonus video when you get a chance. Okay. I have one more video to show you and then we're done. Couple last things to go over for you here. Talking about electrical. I just wanted to show you firsthand. I got a 12 volt battery here in front of me. So I just wanted to go over a couple things and show you guys firsthand how this works. So first thing I'm going to do is grab my multimeter and I'm going to check this battery's voltage. So I'm going to turn it on. Remember, I got my black lead here, my red lead here. I'm going to put it to volts DC. Alright. Hook it up and I got bolts sticking in this battery just for something to tie to. 12.51 volts. 12.51 volts. So that's good. That's a good battery. That's good battery voltage anyway. Okay. So I got all kinds of fun stuff here. First of all, this 12 volt test light, I can't emphasize this enough. This is probably my best electrical tool, diagnosing tool right here. Because I can use this thing. Multimeters are great, but just like that, I got that 12.5 volt reading on this. I've had it before where I measure a circuit, I get 12 volts or whatever. I grab my test light and the thing lights up, but extremely dim. And then I found that there's maybe on a wire that's got, say, 50 strands in it, it's frayed all the way down and there's maybe 1 or 2 strands left. So that's a surface voltage getting through there. But when you actually put a light or a load on it, you're now load testing that circuit. So this to me is doing two things at once. It's load testing the circuit, it's load testing, and it's giving me a reading. So I'm going to touch this right here. That's a nice bright light. Now if I see a dim light, I probably won't be able. So that's a nice bright light. That's what I want to see when I'm testing. But if you take a reading and you get a real dim or real almost a yellowish dim light, you know your voltage is going to be low. You can throw your voltmeter on there, but just by looking at the light, I know what kind of voltage I got too. So I use this all the time. So I got it negative to positive, but it's a light bulb, right? So it doesn't care. I can go positive to negative. It doesn't really care because it's just a light bulb. Alright, so I'm going to show you guys, we're going to build our own electrical circuit right now. So we're going to build our own lighting circuit. Untangle this thing once. Okay. So I got 2 meter leads here. Now, if I touch these two together right now without a load, do you know what would happen? These things would be burnt up in a matter of seconds. They would instantly start to spark and smoke, and the things would get hot and the insulation melt right off of them, because it would be a direct short from positive to ground. But with the use of just a little light bulb here, or an electrical load, we now can safely hook this up. So there we go. We have positively charged electrons coming through this green wire here, going through our headlight. Remember, we're just harnessing the power. It wants to get back to ground. So it's going through this little bulb, through this little light, and it's getting back to its ground. We're making it do work before it gets back there. So right here we have our circuit. That's the simplest circuit you're going to get. Now, one thing I wanted to mention to you guys. We can either go like this to the positive side to turn the light on or off, or go like this to the negative side to turn the light on or off. Oh, that's broken. One thing I typically see more often than not is a vehicle that has a controlled ground side, and it makes sense for this reason. So if you have a light like this, say this is a running light for your front light of your vehicle, you go to do your electrical test and you'll find that there's always 12 volts going to it. Whenever the key's on, you have 12 volts going to it. What you're missing is a ground until you turn your running lights on. Now you got a ground. The reason they call that a controlled ground. So when the power is constant, but the ground is actually, what turns this light on or off. That's a controlled ground. And the reason most things are that way is because there's less electrical energy on the ground side. Because why? Because the load is absorbing some. So with less electrical energy, we have a tendency to we're not going to wear out switches as easily, and we're not going to, that's the biggest thing, we're not going to basically be wearing out our switches as easily, and things are going to hold up better. So the only thing we are missing in this circuit here is a fuse. So now if we wanted to fuse this circuit, easy, all we'd have to do is cut this right here and put an inline fuse. That way, if we ever had a short somewhere in the system, instead of melting the wires, possibly causing a fire, it's just going to pop the fuse. So, anyway, there's that. Okay, what else was I going to show you? One other thing, since I got your attention. When it comes to fuses, we remember, guys, in this job we always have to be detectives, don't we? We're always, when we see something fail, we always want to know why it failed or what caused it to fail. So whenever I have a pop, I'm going to call it, whenever I have a bad fuse or a burnt fuse, I always look real carefully at it. And I'm going to bring this over to show you. So whenever I find a burnt fuse or a popped fuse, and I'm going to explain the difference, I examine it real closely. Because we're always got to be detectives in this job, don't we? So I look at it. Now there's two different ways in which a fuse can go. A burnt fuse or a popped fuse. And a burnt fuse, you'll just see a small burnt spot or a small open in that little fuse element. Where the fuse element, you all of a sudden just see a little open there. A popped fuse is going to be like an explosion happened inside this little fuse. So the difference is, if we have a system that's slowly drawing too much amperage or too much power, more than the circuit can hold, it's going to blow the fuse. It's going to actually burn, it's going to burn the fuse, and we're going to see just a small separation or melted spot in that fuse. When we have a circuit that completely has shorted to ground, it's going to pop the fuse. It's going to look like the element has actually exploded inside there. So just by looking at the fuse, I kind of know what I'm looking for. If that fuse is popped, I know we have a spot of the harness that's chafed right to the ground or right to the frame, something like that. That's causing a direct short, which means a short right to ground. And if we have a burnt fuse, I know we have more of a, that could be a component failure, like say it's your heater fuse, your heater blower motor. Maybe your blower motor's drawing too many amps, or something like that. It's just an example. But another thing, if we look at a circuit, give you guys one more example here of a circuit. Okay, so we had our headlight hooked up here. If we look at a circuit, what we call an open in a circuit is if I would take and cut this wire, right? If I'd cut this wire, we have an open circuit. I could cut the wire either place. We have an open circuit. So another way a circuit can fail is a short circuit. A short circuit, that means a short to ground. Now you can either have a short to ground before or after the load, can't we? So pretend we had a short to ground here. Imagine we had a frame and we had this wire rubbed through somewhere and touch the frame. And if we had a fuse like we should in this circuit, it's going to pop that fuse. And now think about this. If we had a short to ground after the load, what's that going to do? A short to ground after the load. Well, it's going to do this. It's going to turn itself on. It's going to be an uncontrolled circuit. So the absolute funniest thing ever is when that happens to a horn circuit. And maybe you'll be lucky enough to see that. Customer comes in and the horn will not shut off. Pretty hilarious. Short to ground after the load. So whatever, it could be a light, anything like that. If you have something that won't shut off like it's supposed to, you could have a short to ground after the load. So I hope that makes sense. Okay, so now I'm going to show you guys how to repair broken wires. And I hope you can see this okay. I know you can't see my head, but that's even better. So I have a wire lead here that I just cut in half, meter lead, or a test lead. So we're going to repair this wire and make it just as good as new. This is going to be a great example of a repair you can make in a vehicle. If you found a broken wire or a bad spot in a wire, sometimes you can cut out the bad spot and reattach it or hook a new piece of wire in there. So first thing we're going to do is strip the ends. So we're going to take a wire strippers here. Oops. We're going to strip some bare ends on it. I'm actually going to cut this. Strip the insulation off. Okay. So the first wire repair I'm going to show you guys how to do is a solder. How to solder the wire back together. So I'm going to take some of this stuff right here, which is heat shrink wiring. Or I'm sorry, heat shrink. See if I can figure out a way to cut this. Take a little piece of heat shrink. So that's actually going to cover up our solder joint when we're all done. Okay, there. Alright. So the important thing about this, I'm going to take these two ends, and there's a couple different ways you can do it. If you can either mesh these two ends together and try to kind of intertwine the wires just like that. That's a really good repair. The other thing you can do is put the two wires like this. If you're in a tight spot, this might be better. Twist them together. Now solder them. After the solder, though, you're going to have to, try to straighten out the wire and just kind of fold it over, like that. But anyways, so the way I'm going to show you right now is we're going to intertwine these wires together. So I got this little helping hand tool right here. So I'm just going to stick the wire into one side of that. Okay. Now I'm going to intertwine these wires the best I can. Doesn't have to be perfect. I'm just going to kind of roll them around. You just want them to touch, basically. Perfect. Okay. Grab my solder gun here and my solder, and the trick to this is actually getting the wire hot enough to melt the solder. You cannot, if you just melt the solder and let it drip on the wire, it's never going to stick. You actually want to get the wire so hot that the solder runs into it. Okay, it's getting pretty hot now. I usually just start by allowing the gun to warm up until I can get solder to melt on it. Okay, so you can see it's hot enough now that's going to melt the solder. So I'm going to put it right on the bottom of these wires, right on the bottom side of the wire. And it's going to heat up that wire. Then I'm slowly going to touch the solder to it. Now you can see that solder just kind of runs right into the wire. And I'm just going to melt it in there real nice, just like that. Alright, done deal. So now, check this out. Let that solder cool down just a little bit. Let's look at our joint here. Oh yeah, that looks pretty nice. So now, we're going to take this heat shrink, slide it over our solder joint like that. Take my little butane torch, I'm going to melt the heat shrink. Okay, so we'll get that on there. So now we just, if this is a vehicle, by using that heat shrink, you just waterproofed it. So now you're not going to get water or corrosion on your repaired wire. Okay, we'll let that cool for just a minute. And now here's the really cool part. That wire, especially if you use black heat shrink, you can barely even tell. You can barely even tell that wire's been tampered with. And watch this. You want to see if that's a good repair or not? I'm going to try and pull this thing apart. I'm literally trying to pull as hard as I can. That's not coming apart. So that's a good repair right there. Now I'm going to show you guys another way. I'm going to take another piece of wire here. I'm not going to need this anymore. Okay. So the first way we just did was a solder joint repair. The next one we're going to do, so we're going to cut this wire in half and we're going to put it back together. This repair we're going to use butt connectors. So again, we're stripping the ends. Okay, so now we got two bare ends. I'm going to grab my butt connector kit. Now this is from Kimball Tools, which are, these are really nice butt connectors, the best I've used so far. And these are heat shrink butt connectors. So here's my tool. It's ratcheting pliers. And these things are cool because they will not release until you get it tight enough. If you don't have one of those, you can always use a tool like this. These tools, if I'm going to butt connect, I do not want to put it right there. I definitely want to use that end. It's like a crimper end right here. Hopefully you can see that okay. I also like this because it's just, I can get a little bit more leverage out of it. A style of crimpers like this. It's got that same kind of a horseshoe end right there, and you can make some nice tight crimps with it. But I prefer to go with this thing. So I put my butt connector in the tool here, tighten it up. I'm going to put one end of the wire into it. Okay, and I'm going to start crimping. Okay, so there's that. Do the same process for the other end. Okay, we're going to crimp it. There we go. Okay, so we just butt connected this one. That's also a good repair, especially if you use the heat shrink butt connectors. So again, I'm going to take my mini torch here, heat it up, same to this side, heat it up. Now we have a watertight seal. Okay, there we go. And again, that's a good electrical repair right there. That repair in a vehicle would last the lifetime of the vehicle. So, two really good ways to use. You can do whatever you prefer, and also wherever, if you have a real tight spot, sometimes butt connector is better. If you have enough room to work with, sometimes solder's better. It all kind of is what you prefer. So there's that. Hope that helps. Okay, wow, that was a lot to cover, and I know it. Thank you guys for sticking with me. And guess what? We just covered one of the hardest things that you're going to have to deal with in this job, and we made it easy, didn't we? So good job. Pat yourself on the back. We'll see you next time for Module 9, which is engine performance, and we're going to go over everything it takes to make an engine run perfectly. So we will talk to you then.